Hi, welcome to the class. Today's today's video we will discuss about signals, and the course title is Principles of Communication Systems. I am Dr. Dishan Kalim from EC Department, CUI campus. Let's move to the lecture's contents. First of all, we will discuss signals, and then we will discuss the two main categories of the signals. One is called the energy, and other is called the power signals. What are the signals? In general, signals are the detectable quantities used to convey information about time-varying physical phenomena. For example, common examples are the human speech, temperature, pressure, gesture, images, sound, etc. All are signals. And the electrical signals, normally expressed in the form of a voltage or a current waveforms, are some of the easiest signals to generate. Right? Whenever you see the electrical signals, they are usually represented in the form of voltage or a current. Mathematically, signals are modeled as the functions of one or more independent variables. For example, independent variables used to represent the signals are time, frequency, or the spatial coordinates. Let's take an example. These are the music going inside the device, and you will get the audio output. And this is the audio signal waveform, but you get across the time. The variable which we are plotting is the time. So from 0 to 1.2 second, and that we are plotting the normalized amplitude as well. So this is the audio signal waveform. So in general, signals can be any speed, temperature, pressure, etc. And what are the electrical signals? Are usually expressed in the form of voltage or the current waveforms. And energy and power signals. These are the two categories of the signals, and the signals are usually measured in terms of the energy or power. So, when it could be the energy signal and when it will be the power signal, we will discuss these terms in the upcoming slides. So, instantaneous power, as is clearly uh, noticeable from its name, that instantaneous power means that at any time instant, what will be the power? For example, the instantaneous power at time equals to T naught. T naught can be 1, 2, 3, any value of a real valued continuous time signal. If you have a continuous signal, a real value continuous signal xt, and if you want to check the power of that signal at time this time, for example, this is time 2 seconds, then at this point, what is the signal power? So this is called the instantaneous power. And then you will put the amplitude. Power is, for example, this is voltage, because electrical signal is usually represented by voltage. So at the time 2, and for example, the voltage is 4. So 4 square equals to 16 is your instantaneous power at time 2 seconds, right? So instantaneous power at time, this is for continuous time signal, and similarly for the digital time signal or the discrete time signal of a real valued discrete time signal, xt is given by x square k. Here you have a t naught for a continuous time, and here x square k is representing the discrete values. You can say the digital values, right? If the signal is complex valued, the expression of the instantaneous power are modified to x square k, with you have a bar here. This represents the complex value, and you will take the magnitude of these complex values. Right? So in this way you can find the instantaneous power of a signal. And then continuous time and discrete time energy. The other term, important term, is the energy. So energy present in a continuous time or discrete time signal within the given time interval is given by the following. For the continuous time, if you have a two range, for example, from time t1 to time t2, if you would like to find the energy, so x square xt whole square is the amplitude square in interval time t1 t2, with the condition that t2 means the upper limit is higher than the lower limit t1. For example, T1 can be 1 and the T2 can be 3 seconds. So you need to find the energy of a signal between these two times. So this is the representation for the continuous, and similarly for the discrete time we have a summation here, and continuous time we have an integral, and x square k x k whole square in interval k and 1 and 2. Similarly, and t2 should be greater than n1. The total energy of a continuous time signal is energy calculated over the interval infinite interval minus infinity to the infinity. Because for any signal, if you want to calculate the total energy, so you should integrate or do the summation for the infinite interval. The expression of total energy are therefore given as minus infinity to plus infinity. X square xt whole square for a continuous time, and for a discrete sequences minus infinity k equals to minus infinity summation up to infinity x k whole square. So this is the total energy, right? The other term is the average power. The average power, since power is defined as the energy per unit time, we know that power is equals to energy over time, right? E over T, which is very famous equation. So the average power of a continuous time signal over the interval minus infinity to infinity, and for a discrete time signal over the range minus infinity to infinity are expressed as follows. So you would like to calculate the average power. So the duration is infinity, time approaches to infinity over 1 over t. This is 1 over t because energy over time, right? Energy over time. So this is usually energy, and this is over time. So this in this way you can calculate the average power. Similarly, discrete time sequence 1 over 2k plus 1, k equals to minus k to plus k. How this 2k plus 1? Uh, so from this limit you can notice that minus k to k. How many values? 2k, right? Minus k to k, we have 2k number of values. But in discrete time we have another value at 0, right? For example, if you take the discrete time signal, this. For example, k minus k, right? These become 2k. But there is in center there is additional value 0. So we can say that there are 2k plus 1 values, total values, right? So 2k plus 1, we have for averaging, we need to divide by the total time. So in this way we have in this case we have a 2k plus 1. So k equals to minus k to k x k square. So in this way you can calculate the average power. For average power for finite period. Now the only difference in this equation and the previous equation we talked about the infinite period, minus infinity to plus infinity, right? Here we are talking about the infinite finite period, and the period we call T naught. T naught is our fundamental period, so we can just write T naught. So here we don't have a limit 1 to infinity, so we have a total time T naught, which is the period, and starting time can be any arbitrary number t1. So from t1 plus t naught, you know that, for example, this case, right? Here we can call 0 to total t naught. But if we start from another point, not directly from the 0, if we start from here, right, the total time will be same. But the starting point here is t1, so here is t1 plus t naught, right? The period is same, but the starting point is different. So to represent that, we call T1 to T1 plus T naught x t square. Similarly, in the discrete time sequence, we have a total fundamental period k naught. So k naught 1 over k naught. So if we start from any arbitrary k1, so k1 plus k naught minus 1. As I mentioned, there is additional term at 0. So to remove that, we have a k, because here we have a starting at k1, so k1 plus k naught minus 1. So this is the way you can calculate the average power for a finite period. Now the main point is that we discuss power and energy, but what when we can say that this is an energy signal, and when we can uh, say that this is a power signal. So this is the classification, how to classify it as energy or a power signal. So the when you have a signal with non-zero or a finite energy value, this is called a energy signal. Non-zero means it has a 1, 2, 3 any values, but should be less than infinity. If the value of a signal, if you calculate the energy of a signal, and if the energy of a signal came with a finite value, for example 1, 2 up to 10 are within the range of, not range, the for example it comes out 1 or 2 or 10 or 5 or 100 so on, but is less than infinity, and it is called energy signal. And the, if you have a signal with non-zero or finite power value, it's called a power signal. Similarly, if you have a signal which has a infinite energy but finite power, like 1, 2 up to this, then it is called a power signal. And most periodic signals are typically power signals. Here you can find some explanation. If I have it has a E hex, means energy as a non-zero, like 0 to less than infinity, and the other signal is called power signal. It has a non-zero finite power, similar type. Note that the signal can't be both energy and a power signal simultaneously. This is important. So energy signals have a zero average power. So in this case, if this is energy signal, then it will have a, if you will calculate the power, it will give average power, then it will give you 0. Whereas the power signals have an infinite total energy. If you will calculate the energy of a power signal, it will come infinite. So whereas there are some signals which can't be classified as neither a power nor an energy signal. For example, you have a signal E to T, UT. This is a growing exponential. So we can't find the average power and we can't find the energy as well. We can find the energy, but the power energy will be infinite of this signal. Okay, let's take an example. Uh, Consider the continuous time signals. This is xt signal, continuous time signal in A. This is second part B, zt. You have a continuous time signal. So we need to calculate the instantaneous power, average power, and the energy present in the two signals. And then later on, we need to classify these signals as a power and energy signal. By calculating energy or power, when we will have a result, then we will classify them whether these signals are a power signals or energy signals. So let's start with the A, right? Example 1A. We have a signal which lies in between -2 to 2 that have an amplitude of 5, constant amplitude 5, and from 2 to onward this is 0, from -2 to onward this is 0, right? So if we calculate, first we need to calculate the instantaneous power. So instantaneous power, you know that is a signal xt which has a finite value or the constant value in between -2 to 2, which is 5, and we have a 0 otherwise, right? Let's move on. So power of this signal, just square it, as we already studied on the first slide. So square it, so we have a 25, right? This is instantaneous power. Now let's move to the energy. For energy, for example, minus infinity to infinity, 25, and then integrate, so we have a 25t, right? So -2 to 2. So in this way we will get 100, right? And if we go to the average power we need to calculate in the infinite duration. We already studied. So when we put 1 over t energy 100 over infinite, so it will give you 0 average power. So from this we notice that this is energy signal because it has a finite and power is 0. Okay, for the next part B, the signal Z is a periodic signal with a fundamental period 8 and is expressed as this one. We have a constant value of 5 between the range -2 to 2, and for other it is 0. Like 2 to 4 it is 0. So because this has a fundamental period of A, so with Zt plus 8 is equal to Zt, the instantaneous power, average power and energy are calculated as. So instantaneous power is just Zt square, so it is 25. Let's move to the average power. So average power, because this is a power signal, we have a 1 over 8 minus 4 to 4 within the period. So Z square t, just calculate the square 25 over, so 25, if you will 25t. If you will integrate, it will give you 25t, right? So then put these limits 2 to minus 2 because for other part it is 0. So 100 over 8 is 12.5. Whereas the energy we need to calculate for the infinite period. So if you put the infinite values, then you will get the energy as the infinite. Because we from here we can notice that the signal is a power signal because we have finite value of the power, whereas the infinite value of the energy. So that is a classified as a power signal. There is another example. So determine if the discrete time sequence we have a signal gk 3 cos pi k over 10 is a power or energy signal. So we need to determine whether it is a power or energy signal, whereas we have a sequence discrete time sequence. The discrete time sequence gk is equal to 3 cos pi k by 10 is a periodic signal with a fundamental period of 20. How we find that period? Look at this. T, you know that period is T naught over 2 pi f, right? F. Where here if we see cos pi k over 10, so here uh, we have a frequency of pi by 10, right? From there we get pi by 10. By putting this, we get it cancelled. So we will finally get the period of 20, right? By using the discrete time equation, as we know that power is equal to 1 over k naught fundamental period and summation x k square. So equal to 1 over k naught, k is equal to k1 plus k1 plus k naught minus 1 as we already studied x k square. Let's move on. Okay, let's calculate the total power. Pg is equal to 1 over 20, k is equal to 0 to 19 by putting the value of fundamental period 20, and as we have a 20 term including 0, so 0 we have upper limit of a 19. But using that value of 3 cos pi k over 10, so by putting here we get the square as we have a square, so 9 cos square, this is angle, this will have a no square, so pi k over 10, and we can rewrite that one as 9 over 20, k is equal to 0 because cos square theta, as you know that cos square theta by trigonometric identity is equal to 1 plus cos 2 theta, right? Cos 2 theta over 2, right? So using this one here, 1 over 2, 1 plus cos 2 theta, so 2 into pi k over 10. Or let's open this parenthesis and rewrite in two separate times. So we get 9 over 40, summation k is equal to 0 to 19. Here we have a constant 1 plus 9 over 40, k is 0 to 19 and cos 2 pi k over 10. This is, so let's make it two terms, term 1, term 2. But to open this term, there is a one rule. You should have noticed that before, but I mentioned for clarity, I rewrite as a note here. The sum of a constant is equal to n times the constant. If you have a constant here and you now would like to do the summation of this one, so it will be equal to the n times, n here is 20, so 20 times 1, right? So uh, clearly the summation represented by term 1, so n into 20 over 40 because n times into constant, here constant is 1, so n 20 over 40 is equal to 4.5. Whereas to compute the sum of this one, term 2, we can rewrite 9 by 40 by using cos theta equals to e j theta, right? E j theta plus e minus j theta over 2 by using identity. So we can rewrite that term here as this way. So open this one, 9 over 80, k is equal to 0, ej pi 5, 5 by 5 into k, 9 by 80 plus 9 by 80, 0 to 19, e minus j pi 5k. You have already studied that the geometric progression series, because in geometric progression series you have here something like rk. So if you open here in this way, r is ej pi by 5, so it is equal to minus 1 minus ej this one into, instead of k you have here total terms. So total terms are 20. So minus over 1 minus ej pi over 5. So if you are not clear with this, how you is open, so you just refer geometric progression series, and then you can clearly understand how this is equivalent to this equation. Now j pi by 5 into 20, it will be cancelled out, so we will get e j pi 4, right? Whereas if you open this one j pi 4, it will come up as a 1, because by using ej theta, you can write as cos theta plus I sine theta. So cos of pi 4 is 1 and sine is 0. So you will get 1 here. So 1 and minus 1 will be cancelled out. It will be 0. So you will get the 0. Similarly, for this term, e minus j pi by 5k, you will get 0 as well. Here I mentioned minus j pi by 5 4, e minus this similarly by using geometric progression, and e minus j pi by 4 is also 1, so we will get 0 here. So therefore term 2 is equal to 0, so average power is therefore given by 4.5 plus 0 equals to 4.5. So this is a power signal and we have an average power of 4.5. Thank you for listening, and for question answer there will be a separate session, and the exact date and time will be communicated later. Thank you very much.